Loft is my flagship combat robot, historically competing in the 13.6 kg sportsman class. I want to redesign it from scratch with what I've learned over the last 3 events, and prepare it to compete in the open class. This is the highest level of combat in Australia and requires a refined design to have a chance of surviving against powerful spinning weapons. I want to put a lot of detail into covering the design process for this machine. You can't just build a combat robot. Whether consciously or not, one must break down the machine into smaller and smaller problems until they become manageable, as with anything that is engineered. A flywheel flipper is one of the more complicated designs one can choose, and should be an example of how necessary the process is. To spoil the theme of the video, we'll be starting with small problems with few unknowns to try and inform the larger systems that would be very impractical to try and define all at once. I am of course writing this with the benefit of hindsight. The actual process of working up to the final machine was messy with many possible directions to choose. Knowing this, I wrote down the initial ambitions on the drive home from the last event that Mark 1 fought at. Firstly, I wanted a horizontal flywheel, so it can be spun faster without inviting more gyroscopic effects. Next was a cone clutch to increase the system's flipping power, likely actuated by a custom solenoid via a cam. This clutch type would require a fully custom system rather than deriving from the car AC parts, but allow some weight savings by moving away from the heavy electromagnet. The flipper arm should move away from the mild steel weldment for a stronger construction, and have a short arm to keep the tip out of the way of spinners, as well as other mechanical advantages. With what I'll call a plate clutch, the output torque is simply proportional to the coefficient of friction, clamping force, and middle radius on which it acts. A cone clutch uses a tapered surface to amplify the frictional force by wedging the surfaces together. For a given axial force, the normal force is higher the shallower the wedge can be. A big help when designing this, Design of Machine Elements Volume 2, had a section dedicated to cone clutch formulas and practices. As it points out, once the face angle approaches 8 degrees, it will likely end up self-locking and be difficult to extract. This is the phenomenon that many machine tapers use, such as the tailstock in this lathe. One can just push the tapered holder into the smaller hole and it wedges itself in tight, not coming out without the assistance of a screw. I chose 10 degrees for my clutch as this is the lower bound suggested by the book. As a rough example of the benefits, acting with a 10-degree wedge versus a 90-degree plate multiplied the torque capacity by 6, which is a massive improvement. After getting the ideas written down, I always progress to a block CAD. Personally, I need to see things in 3D space, and so want to sketch out the basic parts. It looks something like this, just a quick expression of the key components and how they should fit together. This progresses through to having all the bits to construct a whole robot idea around. In my mind, I had an image similar to Alex Richmond's 12-pound flipper design. I don't think it would have been particularly competitive, but one cannot deny that it looks great. I plan to mimic the swept back frame with a long flywheel module in the center, looking a lot like a sci-fi spacecraft of some kind. While this was the plan, Block CAD A didn't achieve it, too square, boring, and large. I did better with Block CAD B. Overall had similar drivetrain and side armors to derive, but recessed the front to try and keep vertical spinners away. I also considered methods to reduce the volume needed for components by hiding the drive motor controllers underneath the large motors. The plan was slowly taking shape. Parts for this project have been provided to me by PCBWay. This includes the flywheel, cone clutch and hex axle that they all ride on, as well as 3 aluminium frame pieces that would have been very difficult to make myself. Everything was wrapped and padded so they arrived without damage. Steel parts are oiled to keep them from corroding within their plastic bags. Threads in the flywheel and billets look good, and are likely formed with a thread mill tool, considering they all start in the same orientation for an interesting effect. As usual, the bearings slip into the board smoothly with the specified slip fits, so all seems fit for purpose on the robot. At this point, I had to flesh out the flipper module to something that might actually work. Looking for small problems to solve, I knew I wanted a cone clutch to engage the flywheel, and had rough sizings from the block CAD, so modelled that first. Dimensions could be loosely based on the previous functional mechanism, and I reused what worked, a gear drive and hex spline. The system still had a pair of winches that are driven by gears, designed next. Everything is modeled parametrically to make it easy to tweak dimensions in the future, which is a massive time save. Dimensions might move back and forth while the overall machine develops and constraints start to fight for dominance. The concept currently requires a pair of large solenoids. I first picked a target mass with little else to go off of, and you'll need to be longer than it is wide. These needed to connect to the clutch in a manner that can both push and pull. The idea so far is to have the flipper smack something sticking out the back of the solenoids to force disengagement. First shot at this had the solenoids flanking each side and driving a pair of links, pushing down on the clutch when the levers are pulled rearward. As arranged, the small links would increase mechanical advantage as they approached a vertical orientation. The system could be pushed and pulled, so met all initial criteria, but was ultimately unacceptable. The heavy and high inertia links would put large forces on their pins when quickly disengaged. So thinking turned to making a lighter system. Some sort of crank and eccentric arrangement was considered, but this is both difficult to synchronize and gets in the way of the flywheel motor. Without better ideas, the flanking solenoids were deemed a dead end and something else had to be tried. Research led me to some high-power linear solenoids with about enough travel, but they were wide rather than long. The only place to fit them would be in the rear above the winches. The simplest way to connect things is a rocking arm that pushes down on the clutch as the magnet energizes. Both ends have to end up linear, so an extra link is needed to connect them to a rotating lever. With the pivot point biased towards the flywheel, the solenoid force will be amplified as desired. This felt about right. It fits well under the contour of the flipper while being nice and simple. Extending the levers allow the system to be reset by the flipper's end of travel and met all initial criteria. Attention could turn to connecting the winches to the arm rather than relying on a currently theoretical rigging. Loft Mk uses a rack and pinion to drive the arm, which looked cool, but was overweight for the amount of load it could handle. I reckon the Dyneema rope and pulley would be the lightest way of getting the power needed. Before covering version C module, I want to explain a critical design requirement. Kinetic energy is stored in the flywheel in an exponential proportion to how fast it spins. As the flipper fires, the flywheel is going to slow down. In combination with this, if we assume the clutch isn't slipping, the system can't add energy to the opponent if it's not actively trying to move faster. Therefore, we need the system to counteract the slowing flywheel while also accelerating itself to keep pushing the opponent. This is what the rigging currently looks like. It uses a two-part rope system to fire the arm that is driven by the retracting winches. The majority of mechanical advantage comes from the differential winch inherited from Mark I. Take a look at the older videos for a full explanation, but to simplify, the two drums pass rope between themselves at high speed, with one feeding out and one taking in. The drum taking in rope runs at a slightly higher speed, meaning the available slack rope decreases slowly. This has the effect of greatly amplifying the force of a pulley block acted on by the slack, compared to directly attaching a rope to a winch. In this version, the rope is winding through a pulley block attached across a second rope that is also connected to the flipper arms like so. As the pulley block moves towards the winches, the second rope also pulls on the ends of the arms and fires the flipper. This system can achieve a large change in velocity ratio over its travel, which is crucial to fully utilize the flywheel's energy. Velocity ratio is simply a ratio of how fast the inputs and outputs of a system are moving. It's easily visualized with a first-order lever, where the load is close to the fulcrum and the effort is far away. If the effort moves at, say, 3 meters per second and the load moves at 1, giving us a velocity ratio of 3. At the start of the flip, very little rope is moved by the pulley as it retracts, meaning a lot of effort displacement for very little at the load, giving a very high velocity ratio. At the middle of travel, we can see more rope will be moved for a given pulley travel, reducing the velocity ratio. At the end of travel, the amount of rope pulled is almost 1-to-1 with the pulley's displacement. Therefore, so is the velocity ratio. If we line up these states, it should be clear that the perpendicular rope system allows for a continuously decreasing ratio. In practice, it starts at some enormous value for an instant, then decays towards 1-to-1, following a part of an exponential curve. Let's plot all this on a very rough graph for demonstration purposes. We have a line as the flywheel's velocity decays, and another for the changing velocity ratio of the system. If we multiply these, we get the hopeful acceleration of the opponent. So now we have a system that meets all the basic requirements and should behave in an efficient manner. It's dropped into Block CAD C to further flesh out the overall design with the added rigging frame. The machine has shifted back to a more familiar construction method with aluminium rails, with angled armor panels for two reasons. The first, of course, is aesthetics, but ideally, it does not expose any edges for a vertical spinner to grab if ramming them head-on. With a matured flipper module concept, I turn attention to rebuilding the CAD properly. I'll discuss my CAD practices another time, but it generally involves separating each part and subassembly into its own file to bring into a top-level module. Included in this is dealing with clearances, fasteners, and animating it all. This will be Module D. Now the actual robot model can start, with BlockCAD C as a template. This was started well before Derive Mark II, so the drivetrain hadn't been sorted out yet. I'll cover the rest of the robot next time. Around about now, at Loft Feather Mark II version 25, I came to the realization that the flipper module is not a good design. The carbon fiber frame was heavy at 600 grams and took up a large amount of real estate inside the frame. Outside the frame, it was an enormous target, and even in the sportsman class, it would not have survived if the robot was thrown and landed on it. Things had to change. The problem is size and weight. First idea was to ditch the second stage of rigging for rods to directly pull on the sector pulleys and have them run in bushings. The rods could perhaps be carbon fiber to save weight and slide in printed nylon for a super minimal but custom system. Unfortunately, I couldn't get the travel needed without colliding with the flywheel motor, and orienting the rails upwards like on Mark I wouldn't work with the horizontal winches. Next attempt looked into linear rails. The sliding blocks are easy to fixture to, and it seemed small enough to hide in the shadow of the flipper arm. Aside from concerns about the small fasteners needed for the bearing block, this too would collide with the flywheel motor without achieving the desired travel. Clearly, this wasn't going to work. Ideally, there wouldn't be any handoff stage at all, and the winch ropes could act directly on the flipping arm. The first problem was that the differential winch does more passing of rope than it does pulling, and secondly, the ropes need to be more or less in line with the winches to have them wrap correctly. Eventually, after much pondering and idle spinning of the CAD model, I had the idea for Module G. Using bearings, I could force the rope forward enough to clear and line up with the arms, and then could pass the rope all the way around the flipper. Considering how a previous version would retract the pulley and block, this turned the entire flipping arm into the pulley. I'd have to borrow from version 1 to have the variable velocity ratio in which the rope stacked on itself in the fast winch to increase its apparent diameter. Some bearings and braces would also be needed to handle the forces, but I immediately knew that this would be the final module. After a lot of pulling and prodding, designing the parts to support the new rope path, Module G was taking shape. Before long, the new path was implemented, and I couldn't think of a way of making it any simpler. This got dropped into the main robot model, and the machine formed around the newly available space. Aside from the internal volume, there was a much smaller target on the rear for things to hit. I don't expect to handle any punishment besides a few tumbles, so the smaller the better. To actually prove this system will throw the arm, we can sum all the force vectors. Force from pulleys always act in between where the rope enters and exits, so the bearings on the rear of the arm will act at about 45 degrees pointing inwards. Because of the rigid member joining them, the inward component will be cancelled out and only the unbalanced part remains. This acts at approximately 90 degrees to the arm, meaning a torque will be generated to throw an opponent, which is what we want. As for the sector, we can pretend that it is a pulley too. Taking a force direction in between the ropes, it ends up pointing directly towards the arm pivot, which makes sense. No torque will be generated, which isn't helpful, but neither is it counterproductive. It'll amplify the amount of drag at the pivot, but this shouldn't matter too much given how small the pin diameter is. At this point, I decided to do some maths. The plan was to characterize as much as I knew how to, then play with numbers and see the effects. First is to define the clutch, specifically the maximum torque before it slips. The Machine Elements book was again helpful here to provide the necessary formulas. 63 Newton meters isn't necessarily a lot, but the fact that it can act at such high speeds is where the power comes from. Next is the amount of energy the flywheel stores, which is a simple application of kinetic energy formulas after getting the moment of inertia from the CAD model. Applying the stored energy to a 13.6 kilogram mass moving linearly gives the maximum possible speed and height that an opponent can be thrown. In practice, I think I'd be lucky to hit a quarter of this value. Spooling is how long it takes to spin up the flywheel, and one needs to characterize the flywheel motor's torque. Because the motor is being heavily overvolted, but capped with current limiting, it should be able to output the listed torque for most of the spin up before back EMF finally starts to limit it. This incorrectly assumes 30 amps for the entire spin up. I guess the actual time from standstill to full power will take about 4 seconds. Increasing the current limit will of course reduce that time, but I doubt the small motor could reliably handle much more. Perhaps the most useful part of all this is the final section. This calculates how much energy is needed to spin up the mechanism itself, getting the clutch, gears and winch up to speed before any work is done on the opponent robot. By calculating each part's energy needs from the inertia and velocity, we can generate these two graphs. On the left is the proportion of energy each part of the transmission consumes, and on the right is how much energy is taken out of the flywheel to perform that task. Over a quarter of the total flywheel energy is consumed internally, with the majority of that taken up by the clutch. Specifically this part here, the actuating cone, shaft and drive gear. It's not possible to reduce the velocity without also slowing down the flywheel, so the only option to minimize losses is to make it as light as possible. Unfortunately, these parts were already designed to be as lightweight as I could stomach and afford. The best option would be to exchange the steel cone for an aluminium one, the highest inertia part of the subassembly, but it needs decent surface hardness to not wallow out the hexagonal spline. I suspect this is the reason for the very strange spline design in Blip's system, to reduce the surface pressure for a given torque. Having constructed this spreadsheet, I think I can confidently identify the weaknesses of the old Mark I flipper. Primarily, the whole transmission was very heavy with high inertia, particularly the clutch. It had 3 times the inertia of the new design, which would have sapped a very large amount of energy. Even with the meager flips that it did achieve, the flywheel would almost come to a standstill, so that energy had to be going somewhere. It's likely that much went to losses and a slipping clutch, but I'd be confident that the big disc didn't help matters. So, moving back to CAD land, a few changes are made to the module based on what was learnt. A little more material was taken out of the cone clutch to minimize losses, and bearings were put in the flipper sector to keep the rope from burning out when it slides past at 20 meters per second. Gold paint is a necessity and should go well with the white plastic sliders and machined aluminium parts. Black shoulder bolt heads will break up the sheen somewhat. We'll keep a polycarb plate on top to save weight, but have a titanium piece on the front to protect the delicate clutch mechanism from where most attacks will come from. So this is where the flipper module currently sits, ready to be manufactured. There is of course a lot more to discuss regarding the rest of the machine, but that'll wait until the next video. The machine should be ready to compete at Robot Havoc 9, alongside Derive in their featherweight sportsman class. Until next time.